All right, so I will continue and start. Yesterday I was talking about CFT as a quantum theory, first of all in arbitrary dimension, but then I started discussing two dimensions, so let me continue that. And you might remember at some point I introduced, talking about theories in arbitrary dimensions, quasi-primary fields, and promised to mention what are primary fields as well. So we use this name in the context of 2D CFT. So first, let me just quickly recall, we consider holomorphic transformations or analytic ones, which are identified with conformal transformations in 2 dimensions. And if you make such a transformation, then matrix transforms so that it picks up an overall factor. Let me write it like this. And now, primary fields, you can think of them as fields which have transformation properties which somehow generalize this transformation property of the matrix. So, primary field of conformal weight H and H bar is a field which transforms in such a way with H and H bar here in the exponents. And more generally, we can think of this H and H bar as independent quantities, and also think of Z and Z bar, as I mentioned yesterday, as independent variables. So the difference between primary and quasi-primary fields is, of course, that for primary fields we have such transformation for all conformal transformations, and in case of quasi-primary ones, there was analogous transformation, but only under the global conformal group. So that's the difference. So primary field is automatically quasi-primary, but not necessarily in the other direction. Quasi-primary field is not necessarily primary, and one important example, well, we will see if I will have a chance to discuss it in more detail. If so, then I will show that indeed this happens for energy momentum tensor. So this is quasi-primary, but this is not a primary. And yesterday I discussed the form of correlation functions for quasi-primary fields. It was also in general context in any dimension. As a kind of recap of what we did yesterday, I will write analogous formulas now, but specifically in this context of 2D theories and also in the notation, which will be more relevant to what we will discuss in what follows. I will use similar notation as yesterday, so Zij is Zi minus Zj, and now without discussing where this form comes from, arguments are analogous as yesterday, and formulas as well, but for completeness, let me quickly write them down. So up to a normalization, two-point function needs to be of the following form. So that was also similar in any dimension yesterday. The dependence on this Zij is just some monomial, and in fact this is like singular. We have a singularity here, but we cannot have any more complicated function because we do not have any length scale that we could use to take care of dimension full units. Three-point function, and this is also very important quantity. You can think of this C1 to as some normalization. You can absorb it in the form of the two-point function. But C1 to 3 specifies, well, it's specific for a given theory, and this is quite important. And the whole dependence on Z, here are of course parameters Z1, Z1 bar, and so on. So this is such a factor, and analogous one with bars. Okay, and 2- and 3-point functions are fixed up to these constants by conformal properties, but higher point functions are more arbitrary. However, they still have some specific structure. I will also mention how 4-point functions look like. And what is interesting in 2 dimensions is that there is just one independent cross ratio. So in other dimensions, there were 2 of them, 4-point functions, but here we have just one arbitrary parameter, which I call x. I will write in a moment what it is. And the notation is such that this h and h bar here, these are just sums of all weights. And x is the following cross ratio. And in principle, you might form another cross ratio. So you see that these labels in the denominator are different than here. In arbitrary dimension, these are 2 independent quantities, but it happens in 2 dimensions that they are related in this way. So you see that apart from this z dependence, which is fixed, everything depends on x and x bar through one particular function. And moreover, we have also global invariance, which we can use somehow, which has 6 parameters, 6 real ones, or 3 complex parameters, which can be used to send this arbitrary z1, z2, z3, z4 to some specific locations. Standard choice is to choose 0, 1, infinity, and then x. And then the amplitude is fully fixed just by finding the form of this f of x. And we will see later that we will find certain differential equations that in fact enable to determine f of x. And if you look more carefully, analogously you can determine all higher point amplitudes as well. So this also follows from some properties of conformal invariance. So this is just a little appetizer for what will happen later. But it is important to have in mind the structure of these amplitudes as given here. And even more so, I should, regarding the structure, I should stress that from this perspective, you can think of this coefficients, well, up to you, or also this one, but as I mentioned, this you can absorb in normalization. But you can think of it in this way that, in fact, these coefficients characterize a given CFT. Well, these weights are also important. So the weights and these so-called structure constants characterize a given CFT. So much effort, if one is considering some specific theory, is often put into just finding the structure constants, and then, at least in principle, the other quantities in a theory can be obtained from some general properties, like from these differential equations for higher point functions. Okay, so this is one message and kind of extended summary of what I mentioned yesterday. And now I will discuss some formalism which is referred to as radial quantization. It also makes contact with so-called operator product expansion. In quantum field theories. So this is often abbreviated as OPE. And what is quite nice that in this formalism of 2D CFTs, this radial quantization enables to rephrase various computations just in terms of complex analysis. So in particular, various contour integrals are used as computational tools, and then various statements from complex analysis are very useful in getting various results. I will start with a few statements about geometry and also quantum field theory. I'm not sure if these statements are, commonly known, but I cannot derive all of them, so please excuse me if I'm too brief at some points, but I hope what I say will be sufficient. So first of all, I will start by considering coordinates on a two-dimensional space which I denote by sigma 0 and sigma 1 in Minkowski space. It is often useful to consider so-called left or right moving coordinates just as sigma 0 plus minus sigma 1. And in Euclidean signature, which after continuation to imaginary time, this left and right moving coordinates become holomorphic on anti-holomorphic ones. Which I will denote by zeta or zeta bar. And it is also useful to consider compactified space. In particular, in quantum theory, it enables to get rid of certain infrared divergences. So in terms of this sigma, we may think of our space-time just as a cylinder. We have the space dimension along the circle and time direction here. And but
How default this CFT, like this change of topology is not evasive, is that so?
well, for now I will be just considering flat space. And there are indeed important issues when you have non-flat space, but for now let's focus just on flat space. But still, instead of thinking of cylinder, I will now consider a conformal map of the following, well, that's exponential map. So instead of the zeta, I will express everything in terms of what I call z, exponents of zeta, exponents of sigma 0 plus I sigma 1. So this conformal map transforms the cylinder to the complex plane in z variable in such a way that subspaces, constant slices with constant time are circles. Maybe I can add something here. Infinite past becomes the origin. And the future becomes the region at infinity or complex infinity equal time surfaces are circles of some fixed radius. Time translations become dilations. So changing time here, like expands the size of your circle here, and so on. Space translations are rotations, and well, you can analyze carefully what are other changes. Okay, and now to consider a quantum theory, I will just focus on the z-plane here. To consider a quantum theory, I'd like to introduce certain operators which implement conformal mappings, and they turn out to be related to energy momentum tensor. So this is one reason why this is important. In particular, one of its components is Hamiltonian, which implements, in the original picture, time translations, which then become dilations here, which are, of course, a part of the conformal group. And what is quite nice that in this picture, it turns out that also non-zero components of energy momentum tensor are just those which are, well, they can be expressed in terms of holomorphic variables, and they are just holomorphic functions as well. So let me just again focus now on this picture with a flat metric. Let me write also for now z as x plus iy. Flat and Euclidean matrix, so ds square is dx square plus dy square, which I can write as dz bar. And you can see how components of energy momentum tensor in this x and y variables can be expressed using just dz bar. So in particular, well, this is some exercise you should do yourself. I will not derive it, but TZZ and TZZ bar have a bit more complicated form. But what is quite important is that Z bar and Z bar Z components are proportional to the trace, which we know that it vanishes in the CFT. So if you use, first of all, this fact, and moreover, there is also a conservation law for energy momentum tensor. So this statement and conservation law, which looks as follows. If you make, well, some calculation, it then follows that the only non-vanishing components of energy momentum tensor are well, TZZ, which depends only on holomorphic variable z. And this dependence also follows from this conservation law. So this I will call just T of z, and similarly something I will call T bar of z bar, which is this component T z bar, depending on z bar. So this is important that this energy moment, non-trivial components of energy momentum tensor are analytic, and this is also one reason why various computations and the formalism relies a lot on complex analysis. And now, as I mentioned before, this energy momentum tensor should, in quantum theory, generate conformal transformations on various fields. Which are also associated to the certain current corresponding to infinitesimal conformal transformations. So I will not derive the form of this current, but just write what it is, and it simply has the following form. So with this epsilon is a certain infinitesimal conformal change of variables. Then, well, this J of Z is the current corresponding to it. I should have written it more carefully. And then in quantum theory, conformal transformations of the fields can be introduced by commutators with the corresponding charge. I mean the charge corresponding to this current. So what I mean is that if we have some field, let me call it for now psi here, then if we make some conformal transformation and call it by this epsilon, then in quantum theory the variation of the field psi should be given by commutator appropriately understood of this corresponding charge q, which is also called conformal charge. With the same field. And I will also mention in a moment there should be appropriate time ordering taken care of here as well. And then this Q is just integral at fixed time of this current, which in this radial quantization is given by contour integral over the circle of some fixed radius. So this is of the following form, and because now these quantities under the integral are holomorphic, it follows that various tools from complex analysis indeed can be used, in particular contour integrals. Okay, so what we would like to do now is to compute this type of commutator. But as I mentioned, in quantum theory, one should also take care of so-called time ordering, which tells you that if you have product of two operators, then the first one should be taken at the time which is not earlier than the time at which we have the second operator. So in this Euclidean radial quantization, ordinary time ordering translates to so-called radial ordering of operators. Which I will denote by capital R. So if I have product of two operators and then I like to order them radially, then by definition this means either this if modulus z is greater than modulus of w, or the other way around in the opposite case. So more precisely, if I denote this commutator by a star, well, this is how this commutator also should be understood in quantum theory. Okay. And if so, then I can write it a bit more carefully, what I mean by that. By that commutator. So for now, let me ignore the epsilon which is there, which is not quantum operator, but just function or a number. And let me write this commutator in the following form. So I will use this radial ordering symbol and adjust contours appropriately so that it makes sense according to this prescription. So having this commutator would mean that I take t times phi and then subtract phi times t. So I will write both such terms in the same way, but using this radial ordering, t of z phi of w, but adjust contours a bit. Adjust contours in such a way that this radial ordering picks up the proper order of operators. So in the first case, the contour will be such that I have this w, this is the origin, I have this W insertion, and I'd like Z to be of larger modulus than W. So I will.
What's the difference between the first and the second integral?
The contour.
The contour. Okay.
I cannot say what this quantity is before I choose proper ordering. And this ordering depends on how large is the modulus of Z or W. So in this first case, I take the following contour. I integrate, sorry, I need dz, of course. In this first take, I take Z to have a bit larger modulus, well, larger, but I can schematically draw it like this. So I want to this Z to go beyond W. And in the second case, I consider the opposite. Sorry. This is the origin. This is W. And the contour is like that. And now, using what we know from complex analysis, I can indeed write these two expressions as a single one with the same argument, but with the contour, which is a difference of these contours here, which brings us to the point I want to make. And now the contour is just encircling W. So here we had large contours, and Z in principle was far from W. But here, in this expression, we have Z very close to W. And this is a very important feature, because in quantum theory, where you have two operators which are inserted very close to each other, then you can write what I referred to earlier in the title. You can write their operator product expansion. So from this complex analysis arguments, it follows that we can use this OPE in this context as well. OK, so this was like a side computation, but now let me go back to this full commutator which I had here. So variation of phi. Now in this side computation, I just used Z and W without Z bars and W bars, but more properly, let me now use both of them. So just using this argument above, I can write this commutator again using these two expressions, and then write them as a single expression with this contour with Z being encircling W. So on one hand, I can write it in the following way. Here I have the same contour C. And, well, there is analogous part for barred quantities. So this is one expression I can write using all this. But then I can also write the form of this variation, if this is now primary field, well, in that blackboard I was quite general. I mentioned that variation of any field is introduced in this way. But let me now consider phi to be a primary field. So I started this lecture, I erased that already, saying how a primary field transforms. So let me just remind you what I wrote in the beginning was well, this expression that phi goes to df dz to power hd, f dz bar to power h bar, and then phi. This is the global transformation. So then it follows that local one, you also need to make this computation yourself. It follows that local transformation okay, sorry for running between blackboards, but I can write it immediately here. It follows that the local transformation takes the following form. Okay, so these are unbarred, these are barred quantities. And of course, it follows from looking at the expansion of that to first order, and then this h and h bar, which are in the exponent, arise here as overall factors. So for a primary field, you would like this expression. So this contour integral, which when you compute, in fact, what you do, you just pick up residues. You would like to be equal to this thing. And from the statement, you can deduce what should be the form of what you have under integral here. Oh, just the derivative with respect to W. This one. Just the derivative of epsilon, which is a function which implements, I mean, some conformal change of coordinates. Okay, so from...
Differentiate epsilon with respect to W.
Yes. Yeah, here you mean. This is the derivative with respect to W bar, and this is just the W.
How do you relate epsilon to F?
Well, epsilon is infinitesimal form of transformation. So you look at, and F is the, that's the global, I mean not global, but not infinitesimal.
Is it clear that this current with epsilon dependence turns Z into Z plus epsilon? Is that obvious? Because that's what you're using to make this claim, right?
Again, sorry?
Is it clear that the Z prime is Z plus epsilon based on what you've written on that board?
Well, this, not completely. This epsilon needs to satisfy certain conditions because this is just for conformal transformation. So this epsilon is not completely arbitrary, but it needs to satisfy certain conditions, which I don't think I wrote them explicitly. I mentioned them yesterday.
Yeah, but sorry, but yeah. So how do you read off that?
Yeah. So indeed, that would be that. Okay. So now consistency between these two expressions means that this quantity with z and w being close to each other has the following form. And then there may be other terms. So when you compute these contour integrals, in particular, we pick up these terms, which give rise to these two terms. And similarly for bar quantities. Okay. And possibly terms which are non-singular. So such expressions indeed are called operator product expansion, again, as I mentioned before. So let me say again, here we have two quantum operators. You want to compute their product with arguments being close to each other. And then you see that this product is in fact expressed as some combination of operators for primary field, which are just this field phi or its derivatives. So in this way, in this radial formalism and using complex analysis, you can then use properties of OPE. And this is very important property of primary fields. So let me again stress that what I wrote here is just for primary fields. And in fact, you might also use such a statement as a definition of primary field. I try to introduce this field in some other way and then make some computations from which this property follows, but you might again try to formulate CFT just by saying that this is a defining property of what primary field is. And it is also important that OP is equivalent to canonical commutations of modes of the field. So maybe this is something you are more familiar with. Well, it depends on a theory, of course. You may take boson or fermion or whatever. And I just mean that if you know the OPE for a given field, then you can deduce what should be commutational relations of the field. We will see that also in what follows. And you can also think of this OPE or reinterpret it as behavior of fields under correlation functions. So if you compute some correlation functions and you have two operators with arguments close to each other, then you can replace them by such right-hand side of these equations under the correlation symbol, and then compute it just using these fields and not those products. Okay. So you see, we got this OPE just in a very specific example where I have energy momentum tensor and primary field, but I also do not have time to introduce that in general, but you, of course, imagine that this happens for various other fields as well. So another example, or maybe let me write one more general statement. Yeah, what is also important, and you see in that example, that when you take the product of these two operators, then certain singularities occur. I mean, you have this z minus w in the denominator. So indeed, singularities may occur when operators approach each other. And are encoded in this operator product expansion. So I will often write it in the following way. A product of two fields can be replaced by the summation, where we have here some numerical coefficients. I mean numerical in a sense that these are not quantum objects, and possibly singular and here, in principle, operators which form the complete set of operators may appear. So as I mentioned in the definition of what I understand by conformal QFT yesterday, this complete set is the set of well, various operators, in particular primary ones, and also their derivatives. And one more example I will mention: if we take two primary fields, or not even primary. Let me write it in the following way. So if you take the operators with fixed I conformal weight, and compute their OPE then we get some coefficients here. And then dependence on the z and w, which is just fixed by these weights. And then phi, some other fields, phi k, with this phi k has, of course, weight hk. And then important statement is that this c, I, j, k, they coincide with the coefficients which appeared in 3-point functions.
So there are no Dirac steps
at least not in CFTs. Okay, so I should stick at 3 minutes, up to 5, hopefully, because it was hard work a bit. But now we can take advantage of what I mentioned here. Oh, and by the way, yeah, I will often, in what follows, ignore this symbol of radial ordering. So I didn't write it here on purpose, because we will write many such OPEs, and writing R all the time would be a bit well, disturbing and making the formulas even longer. Okay, so now using the same formalism and techniques and so on, I will hopefully in 3 minutes write something which is also used in other contexts and probably will be used in other lectures, which is called conformal word identity, which is the statement how amplitude, which involves energy momentum tensor and several fields, primary fields, behaves. So let me now take a number of primary fields at locations W1, W2 up to Wn, and the circle, I mean contour which encircles them. So to compute such an integral, I will replace it just by integrals around each of those points. Using this contour argument which I used before. So if I'd like to compute now analogous expression as I had before, then if the initial integral here is this integral over large radius, I can replace it by integrals around each of the points. Let me call them these contours here C1, C2, and so on up to Cn. So this will be over contour Ci. And now, because I have this contour just around a given point, I can use the OPE of T with phi, which we know how it looks like. This is just given there on top.
CJ, right?
Of course. And so I can replace this by that OPE, and then because it should work for any epsilon, well, not quite any, but for all epsilons that implement conformal transformations, then I can also, by arguments often used in complex analysis, I can get rid of these integrals and then use the form of the following expectation value. So when I take this OPE, I get those, the terms which give non-trivial contributions are those singular ones. If I compute, I mean, I can then take out of the, I mean, sorry, I'm just ignoring the integral because it should work for an epsilon. So I simply get the following expression. I may take them dependence on z and w out of the expectation value. So for each of those insertions, I have the corresponding weight, z minus wj, where c is the location of this t of z. And here the derivative with respect to wj, and then expectation value involving just those primary fields. Because here there is no more t of z because I got rid of it using this OPE. So you see that if you know this amplitude, you can immediately obtain the amplitude which involves insertion of some extra operator. And there are many other identities of that form. I just wrote down this one, but well, other ones can be found similarly. Okay, and I think that's the point where I should stop. So thank you for now.
You're just missing a square.
Oh, thank you. I am missing a square. That's a good point.